Hello all. In this and the next video, we will take a look at the estimate sequences framework, which is a different approach to finding the oracle complexity of algorithms. It is a general approach and can be used to construct a broad range of algorithms beyond the accelerated gradient descent. Before starting, we mentioned that in these videos, we will consider a different representation of accelerated gradient descent compared to what we saw in the earlier videos. In particular, we will be considering the following algorithm. So we initialize with some arbitrary x1 and set z1 equal to x1. Then at the tth iteration, we calculate beta t such that L beta t square is less than equal to 1 minus beta t into gamma t, and calculate gamma t plus 1 as 1 minus beta t times gamma t. Then the updates take the form yt equal to 1 minus beta t xt plus beta t times zt, xt plus 1 equal to yt minus 1 over L gradient f of yt, and zt plus 1 equal to zt minus beta t by gamma t plus 1 into gradient f of yt. This form is interesting because you can see that we are maintaining two different iterate sequences, xt and zt. We take a step along the negative gradient, but in one case we are starting at yt and in the other case we are starting from zt. And finally, we take yt as the convex combination of these two steps. The algorithm is actually exactly the same as the accelerated gradient descent discussed earlier, but expressed using a different notation. Therefore, its complexity is also same. This form has also been used in this reference below to obtain further geometric intuition about the accelerated gradient method. To see the equivalence between the two methods, we need to do some manipulations. First, assume that we are selecting L beta t square is equal to gamma t plus 1, which is equal to 1 minus beta t times gamma t. Then we actually eliminate zt, since zt plus 1 can be written as yt minus 1 minus beta t into xt divided by beta t minus beta t by gamma t plus 1 into L times yt minus xt plus 1, which can be written as 1 by beta t xt plus 1 minus 1 minus beta t by beta t into xt. So if we substitute this into the expression for yt plus 1, we obtain that yt plus 1 is equal to 1 minus beta t plus 1 into xt plus 1 plus beta t plus 1 into zt plus 1, which can be written as 1 minus beta t plus 1 plus beta t plus 1 divided by beta t into xt plus 1 minus beta t plus 1 into 1 minus beta t divided by beta t into xt, which again can be written as xt plus 1 plus gamma t plus 1 into xt plus 1 minus xt, where we have set gamma t plus 1 to be equal to beta t plus 1 times 1 minus beta t divided by beta t. So you can recall that this is exactly the update equations that we considered for the accelerated gradient descent method. Also, we can select beta t in the same way, since beta t plus 1 square is equal to 1 by L 1 minus beta t plus 1 into gamma t plus 1, which is equal to 1 minus beta t plus 1 into beta t square. So this is exactly what we had earlier when we were choosing beta t. We begin with describing the basic idea. For simplicity, we will consider the unconstrained problem x star is equal to arg min over x f of x, where f is smooth and convex. So we have the following definition. Consider the sequence phi t, lambda t, xt, where phi t from v to r is a sequence of functions. Xt are the iterates of the algorithm, so they belong to v. And finally, lambda t is a positive valued sequence. This sequence is referred to as an estimate sequence for the function f if it satisfies f of xt less than equal to phi t of x, which is less than equal to 1 minus lambda t f of x plus lambda t times phi 1 of x. The reason we have defined the sequence of functions in this way is that if we write down this inequality for x equal to x star and subtract f of x star from all the sides, we obtain that f of xt minus f of x star, which is the optimality gap, is less than equal to phi t of x star minus f of x star, which is less than equal to lambda t times phi 1 of x star minus f of x star, which is basically order lambda t since phi 1 of x star and f of x star are constants. So the intuition for phi t of x should become clear from this relationship. We can say that phi t are essentially approximating f, and the quality of the approximation gets better and better with t. Note that the right hand side depends on x star, so it is a constant with t, and therefore the optimality gap is order lambda t. So in other words, we can find an estimate sequence where lambda t decays as fast as possible. Then we can immediately obtain the required convergence rate. The definition gives us the key idea behind the estimate sequence framework. We start by assuming a parametric form for phi of t. For instance, quadratic functions are often used. Then we would need to find out what parameters which will give us the exact phi of t we need to choose such that it is a valid estimate sequence and satisfies both the upper and lower bounds in the definition. As already stated, we would need to figure out how xt is updated, and that should give us a way as to what the corresponding algorithm is. Therefore, this is a constructive proof of the accelerated gradient descent. Next, we show that it is possible to specify phi t in an alternative fashion such that the upper bound condition is satisfied. So the result is that the sequence of functions defined iteratively as phi t plus 1 of x is equal to 1 minus beta t times phi t of x plus beta t times L of x comma yt, where beta t is greater than 0 and L of x comma y is a lower bound on f of x, such that f of x is greater than equal to L of x comma y for all y. This sequence satisfies the upper bound property, that is that phi t of x is less than equal to 1 minus lambda t f of x plus lambda t of phi 1 of x, where lambda t is equal to product from I equal to 1 to t minus 1, 1 minus beta I, and lambda 1 is equal to 1. This statement therefore gives us a way of constructing estimate sequences. The lower bound that we have required here can actually be chosen easily using the first order convexity condition. So L of xy is equal to f of y plus gradient f of y comma x minus y. So this is true for convex functions, and in case you have strongly convex functions, we can use the quadratic lower bound as well. So L of x comma y is either linear or quadratic. For most of the results in this video, we will make use of inductive proofs. So first we need to verify that the condition holds for t equal to 1. That is clearly true because lambda 1 is equal to 1. So it holds that phi 1 of x is less than equal to 1 minus lambda 1 f of x plus lambda 1 phi 1 of x. Actually, equality holds in this case. And this is true for any f and phi 1. The next step in any inductive proof is to assume the required statement holds for t. So which is that phi t of x is less than equal to 1 minus lambda t f of x plus lambda t phi 1 of x. So we need to assume that this is true for some t which is greater than or equal to 1. This is called the induction hypothesis. Under this hypothesis, we will therefore try to prove that it is true for t plus 1 as well. We proceed by expanding phi t plus 1 of x is equal to 1 minus beta t phi t of x plus beta t times L of x comma yt, which is the given form. Next, since L is a lower bound on f of x, it follows that the right hand side is less than equal to 1 minus beta t into phi t of x plus beta t into f of x. Now we add and subtract 1 minus beta t into lambda t f of x, so as to write the right hand side as equal to 1 minus beta t into lambda t into f of x plus 1 minus beta t into phi t of x minus 1 minus lambda t f of x. The reason we have added and subtracted this term is so that we could use the induction hypothesis, which implies that the right hand side is less than equal to 1 minus beta t into lambda t into f of x plus 1 minus beta t lambda t phi 1 of x, where we have used the bound in the second term. So we can see that it is indeed in the required form, and in fact we can write it as equal to 1 minus lambda t plus 1 into f of x plus lambda t plus 1 into phi 1 of x, where we have defined lambda t plus 1 as 1 minus beta t into lambda t. And if we expand this recursively, we can see that this is equal to I from 1 to t product of 1 minus beta I. So that is all for this video. We have introduced the idea of estimate sequences and have also seen a recursive update rule that allows us to construct a class of estimate sequences that satisfy the upper bound property. Now it remains to satisfy the lower bound property as well.